Hello friends, my name is Dr. Avinash Vishwakarma and today's my lecture will be on de Broglie hypothesis or matter waves. So the hypothesis of de Broglie was given in 1924 which is also named as matter waves. But this hypothesis, before going to start this hypothesis, let us talk some historical development. So before the experiment of before the photoelectric effect or black body radiation, the light, or we can say the electromagnetic radiation or radiation, was considered as having a wave property with that was verified with the Maxwell's theory. The properties like diffraction, interference and polarization, which shows the wave nature of light. But after the 1900, after the Planck's black body radiation law and Einstein photoelectric effect, then after that Compton effect and pair production effect, it was considered, it was verified that light is having a particle nature also, or radiation is having its particle nature also, as well as its wave nature. Means a light light is have wave particle duality, or we can say the radiation have wave particle dualities. In some cases it will show its wave property, and in some cases it will show its particle property. So using this concept, de Broglie has given his hypothesis when he was doing his PhD, and he has given his theory in 1924 that if light has wave particle duality, then or the radiation have a wave particle duality, then this law should be universal and it should apply in nature. It should apply in nature for every material object. So he has given his theory that every moving particle will have its associated wave property in addition to its particle property. So in this way he has given his hypothesis that any moving object will have its wave associated wave nature also, or we can say that material in a motion should also display its wave nature in addition to its particle nature. So when I am saying that its wave nature, that means that moving object should have something wave property, and for the wave property it should have its wavelength, and that wavelength of wave will be related to the particles object's momentum. So this lambda is known as de Broglie wavelength, and that wave nature which is associated with the moving object means that wave property named as de Broglie waves, and this relation is named as de Broglie relation. If you look at this relation, then in this relation we will see the wave and particle duality both, because P, which is representing the momentum, it shows the particle nature, and lambda, which is showing a wavelength, it shows its wave nature. So in this relation wave particle duality exist. So that is why this relation is very important. So lambda is the de Broglie wavelength, and similarly we know in the case of photon, we know the energy of photon is equal to hν or light or Sc by lambda. and we can write E is equal to PC. Then here from this relation we also will get that E is equal to lambda is equal to H upon P. So this relation of photon, where lambda is representing the wavelength of photon and P is representing the momentum of photon. So this relation is also holds this de Broglie relation, or this relation is true for the de Broglie waves. So in this way this was confirmed that this wave particle duality of light will be applicable to the any material object which is in motion. So in this way any moving object will have its associated wave nature, and that wave will be called as a de Broglie waves, or we can say matter waves or group of waves. Okay, so this wave will be something like this, and this is known as group of waves. Here is the wavelength of that wave. So this is named as group of wave, and this amplitude representing that finding the probability of finding the particle in between here or here or here. So that means if we have some object which is in motion, if I throw this object with some velocity v, then there will be associated wave property also around this object, and that wave will be known as matter waves or de Broglie waves, and the wavelength of that wave will be lambda is equal to H upon P, where P is the momentum of that object. In this way this relation shows the wave particle duality of that object, because one side of equation is showing the wave nature and one side of equation is showing its particle nature, its momentum, or we can also write this equation lambda is equal to H upon P is equal to mb. Okay, so we can write this equation in terms of kinetic energy also. We know formula for the kinetic energy, Ek is equal to half mb square, or we can write this p squared by 2m for a non-relativistic particle or classical particle. ठीक है, तो when Ek is equal to then from here we can write this P is equal to square root of 2m Ek is the kinetic energy. Then the this relation will be lambda is equal to H upon square root of twice me in terms of kinetic energy of that particle. This will be de Broglie relation. But what will be de Broglie relation in case of electron which is having some potential? For example, we have electron and we are accelerating this electron with some potential v, then the kinetic energy of that electron will be E into v, and this is the Ek. Then in terms of electron we can write this relation lambda is equal to H upon square root of twice mev for the electron accelerated with the potential v. This will be de Broglie relation. So why this de Broglie hypothesis is important? This de Broglie hypothesis is important because according to this, particle object which is in motion so display its wave property in addition to its particle property. So after that, before this de Broglie hypothesis, we know about the electron, but we consider electron is having as a particle nature. The discovery of electron was discovered in 1897 by J.J. Thomson, and during his experiment he has has told that electron is having a particle nature. But after this de Broglie hypothesis, it was considered that electron should also display its wave nature, and that wave nature of electron was confirmed in 1927 by the scientists, which is known by the scientist Davison and German, where he has confirmed that electron is having its wave nature also, because they have performed in their experiment. They have in their experiment they have found that electron was diffracted through the nickel crystal. So this diffraction phenomena was showing the wave property of electron. So in this way, this was confirmed in 1927, and at the same time in 1927, G.P. Thomson, who was the son of J.J. Thomson, he has also confirmed that electron is having its wave property through the experiment of diffraction of electron with the thin films. Means electron are projected on the thin films, and there will be scattering of electron, and that scattering of electron will show its diffraction, and in this way wave nature of electron was confirmed with the experiment of Davison German and G.P. Thomson experiment. And then after in 1929, de Broglie was given Nobel Prize for his discovery. In 1929, de Broglie was given Nobel Prize for his discovery because after this experiment, the same term which we can term you know, electron microscope. So electron microscopes के थ्रू हम लोग wave in electron microscope, the electron was considered as a wave, and that is why we were able to explore the atoms inside the crystal, because it was having wave property of electron. Now the question is, if the particle is having a wave property or de Broglie waves, then when we will see if any object have wave particle duality, then when we will observe its wave nature and when we will observe its particle nature. So when the de Broglie wavelength will be in the order of particle dimension, then we'll observe the wave nature of that particle. If the de Broglie wavelength is very small compared to the atomic dimension, they will observe the particle nature. For example, if I have a ball which have some mass 0.101 kilogram, or we can say 10 gram, and it has some velocity v, 10 meter per second, then the de Broglie wavelength will be 6.6 into 10 power minus 34 upon 0.010 kilogram into 10 meter per second. So here the order of this will be around 10 power minus 3, 10 to power minus 32 meter. This will be de Broglie wavelength order, and and the mass of that ball is 0.1 kilo, and the order of will be 1 meter or 2 meter, suppose, diameter of that ball. So here this de Broglie wavelength is very small compared to this size of the ball. So here it will not represent its wave property. Wave property will observe only when the de Broglie wavelengths will be in the order of, will be comparable to the particle dimension. For the case of electron, if I have electron which is moving with some velocity 10 to the power 7 meter per second, and it is being accelerated with some potential of 10 electron volt, then the kinetic energy of electron will be 10 electron volt. Okay, and mass will be 9.1 into 10 power minus 31. So here we can calculate the lambda equal to 6.6 into 10 power minus 34, जिसका 2 9.10 minus 31 into 10 into 1.6 10 power minus 90. So if you solve this relation, then you will see that the order will be around something in the range of angstrom. So if de Broglie wavelength is in the order of angstrom, and we know that in a atom the interplanar spacing in a crystal, the interplanar spacing is around the angstrom level. So that is why in for the crystal we can use electron as we use in the TEM, where electron is used for the resolution purpose, because its wavelength is in the order of dimension interplanar spacing. So this was the overall de Broglie hypothesis. Why it was relevant, I have told you. Okay, thank you.